Chapter 14, Chemical Kinetics. Kinetics studies the rate at which a chemical reaction or process occurs. Besides information about the speed at which the reaction occurs, kinetics also sheds light on the reaction mechanism, exactly how the reaction occurs. 4 different factors affect the rate of a chemical reaction. First of all, the physical state of the reactants. In order to react, the molecules must come in contact with each other. The more homogeneous the mixture, the faster the molecules can react. In other words, the more surface area you put out there, the faster something will react. Secondly, concentration of reactants. As the concentration of reactant increases, so does the likelihood that the reactant molecules will collide, and therefore higher concentration equals higher reaction rate. Thirdly, temperature. At a higher temperature, reactant molecules have more kinetic energy, they move faster, collide more often, and with greater energy. So higher temperature, higher reaction rate. And lastly, the presence of a catalyst. Catalyst speeds up reactions by changing the mechanism of the reaction. We'll study those towards the end of this PowerPoint and the last video cast that you watch as well. We're going to focus in on the second one. We're going to take a closer look for the next number of slides on how concentration affects the rate of a reaction. Catalysts are not consumed during the course of a reaction. Rates of reaction can be determined by monitoring the change in concentration of either reactants or products as a function of time. So change in concentration divided by the change in time is what we're going to be looking at. In this reaction, the concentration of butyl chloride was measured at various times, and you can see here, as time goes along, concentration of butyl chloride decreases. That's because it's used up and it's made to become this other stuff. The average rate of the reaction over each interval is the change in concentration divided by the change in time. Remember, triangle means change, so we look at change in concentration divided by change in time. That is the average rate. Note that the average rate decreases as the reaction proceeds, and that kind of makes sense because there's less of this stuff, less collisions of it, so the rate decreases as you go along. This is because the reaction goes forwards, there's fewer collisions between the molecules. I just said that. Here's a graph of the reaction rate and a plot of concentration versus time for the reaction, and it yields a curve like this. You can see that concentration decreases as time goes along and is nonlinear. It's nonlinear. Slope of a line tangent to the curve at any point is the instantaneous rate. Notice that it's a point on the line, and then we draw a line tangent to that point. Find the slope of that line, and it's the instantaneous rate. Here, right here, we're drawing a line that's tangent to the initial concentration. They call this the initial instantaneous rate, which we'll study in depth here in a moment. All reactions slow down over time, therefore the best indicator of the rate of the reaction is the instantaneous rate near the beginning, and that's the one we're going to look at, not so much the average rate, but the instantaneous rate at the beginning. Reaction rates are also stoichiometrically equivalent. In this reaction, the ratio of C4H9Cl to C4H9OH is a 1-to-1, so as one disappears, one appears. You can see right here that when we say disappears, we put a negative sign right there, and then as one appears, we leave it as it's positive. So what if the ratio is not 1-to-1, like 2-to-1? For every 2 of these that disappear, 1 of each of these appears. And therefore, we can write a general equation like this that allows us to relate the stoichiometry to the disappearance and appearance of reactants and products in that order. In general, then, here's the general equation. And now we're going to look specifically at concentration and rate. One can gain information about the rate of a reaction by seeing how the rate changes with the concentration. And here we're going to take a look at a number of pieces of data from an experiment that involves ammonia and the nitrite ion. And you can compare experiments 1 to 2. Notice nitrite remains the same. NH4 doubles. What happens to the rate? 5.4 to 10.8. It also doubles. Likewise, comparing experiments 5 and 6 right here, you can see NH4 remains constant. NO2 doubles. What happens to the rate? It also doubles. We can use this concentration and rate data to help us determine something called the rate law. The rate law is an expression, a mathematical equation that looks like this, where rate is equal to some constant k called the rate constant times the concentration of each reactant to a certain exponent. There's no exponents written here because the exponents for this are 1. because if you double the concentration, you double the rate. That means it's a single exponent of 1. This K, remember, is called the rate constant. This rate right here is just a rate in molarity per time, or molarity per seconds. A rate law shows the relationship between the reaction rate and the concentration of reactants. The exponents tell the order of the reaction with respect to each other. Get used to this word, order. Order means exponent in terms of rate laws. And the reaction is first order in NH4 plus and first order in NO2 minus, because the exponents there are 1 and 1. Remember, an exponent of 1 you don't have to write because everything's assumed to have an exponent of 1 to start with. The overall reaction order can be found by adding the exponents in the reactants in the rate law. This reaction is second order overall because it's a 1 plus 1. We're now going to take these rate laws, or rate expressions, where rate is equal to some constant K times the concentration of something to some power, and we're going to perform some calculus on them. You don't have to know the calculus, you just have to know the resultant equations. For a first order rate process, something that has a exponent of 1, if we perform integration on that equation, we end up with this equation right here. This is called the first order integrated rate law equation, where A0 or A0 right here is the initial concentration of A, and AT is the concentration of A at some particular time t. K is the rate constant, and LM stands for natural logarithm. Look for that on your calculator. Manipulating this equation allows us to write it in this form, where natural log of A at some time is equal to negative KT plus natural log of A0, or A0, or A original. I like to think of this as a O because it's the original amount. This takes the form y equals mx plus b, and notice it's got a negative slope, and the rate constant is the slope. Therefore, if a reaction is first order, a plot of natural log of concentration versus time will yield a straight line with the slope being the negative rate constant. First order processes always fit this. Therefore, if you have rate equals some constant K times the concentration of something to the first power, it will always yield a straight line with a negative slope when graphically you take the natural log of the concentration and graph it versus the time. Here's a first order process where methyl isonitrile is converted to acetonitrile. Here's the data. You can see pressure right here is used instead of concentration, and as long as it's a gaseous reaction, pressure and concentration are analogous to one another. Notice it's not a straight line because it's just the pressure versus time. But if we graph the natural log of the pressure versus time, now we get a straight line with a negative slope, and therefore we can tell that it's a first order process. By graphically looking at the natural log of the concentration versus time and getting a straight line with a negative slope, we can find out that it's a first order process. And you can find the slope of the line to find the rate constant. Similarly, integrating the second rate law, one that has rate equals some constant K times the concentration of something in the second power, you get this equation right here. This also is in the form of y equals mx plus b, but notice that the y-axis will now be 1 over the concentration. And the x-axis once again is time, and the slope is K. This is an incorrect sign right here for the second order. It should be a positive sign right here. Please fix that in your PowerPoint packet. They've got it screwed up here. So you can see here it'll give you a T with a straight line, and the straight line is K. Here's an example of a second order process. They give you some data, graph the data, and notice it's not a straight line when you do natural log of concentration versus time. But then if we do a 1 over concentration versus time, you can get a straight line with a positive slope. Okay, 1 over concentration versus time gets a straight line with a positive slope. This positive slope right here is K, the rate constant for that second order process. You can find the half-life of a first or second order process, and it's defined as the time required for 1/2 of the reactant to react. And you can see if we start with 150, when we get down to 75, that amount of time right there is called the half-life, the amount of time it takes until you have half its amount left. In a first order process, you can plug this into the integrated rate law equation and solve for T1/2. T1/2 then becomes the natural log of 2 divided by K. Notice it's independent of the amount of stuff that you start with. This equation is not given on the crappy periodic table, and therefore you got to memorize it. Not tough to know. ln2 divided by K. More about that in future video casts. First order process does not depend on the original amount. contrary to a second order process. In a second order process, you can see that the half-life does depend on the original amount of the substance. You can see T1/2 is equal to 1 over K times A naught. This also is not given on the crappy periodic table. Neither is the second order integrated rate law equation. Moving along now to a second factor that affects the reaction rate, and that's temperature. Generally, as temperature increases, so does the reaction rate. You can see it graphically right here. Temperature goes up, reaction rate constant also skyrockets. This is because K is temperature dependent. In a chemical reaction, bonds are broken and new bonds are formed. In the collision model, molecules must collide to react. Secondly, you have to have the correct orientation. You can see right here that if they collide correctly, you can make two new substances after a collision. If they don't collide with the correct orientation, though, you're not going to have a reaction. Those two factors describe something called the minimum amount of energy required to create a chemical reaction, called the activation energy. Just as a ball cannot get over the hill if it does not roll up the hill with enough energy, a reaction cannot occur unless the molecules possess sufficient energy to get over the activation energy barrier. Sometimes this is a spark, a lighted match, something to just get the reaction going. It's helpful to visualize the energy change throughout a process on a reaction coordinate diagram like this one. This one happens to be the reaction coordinate diagram for the rearranging of methyl isonitrile. Notice we start with a certain amount of potential energy, which is on the vertical axis right here. And then the horizontal axis is the reaction pathway. Some people think of it as time, but it doesn't necessarily have to be that. Notice you have to obtain a certain amount of energy right here. It's called E sub A, the activation energy, before the complex can reach what's called the activated complex and split, and then it can react and form the new product, whatever it is. The start to the finish is the enthalpy of the reaction. The enthalpy of reaction. Notice that it ends with less than what it started with, so it would be an exothermic process. The high point is called the transition state, where the activated complex is created, and the gap between the reactants and the products is the activation energy barrier. Temperature is defined as the measurement of the average kinetic energy of the molecules in a sample. And at any temperature, there's a wide distribution of kinetic energies. When you increase the temperature, though, you can notice you lower this fraction of molecules that will not react, and you shove more of them over here that meet the minimum energy needed to react. And so higher temperature generally means more with a certain amount of activation energy that allows it to react. As the temperature increases, the curve flattens and broadens, and thus at higher temperatures, a larger population of molecules has higher energy. If the dotted line represents the activation energy, so does the fraction of molecules that can overcome the activation energy barrier. As a result, the reaction rate increases with temperature. This fraction of molecules can be found through an expression. This expression was further modified by savant Arrhenius, and he came up with an equation called the Arrhenius Equation. A is the frequency factor, E sub A is the activation energy, R is the universal gas constant, T is the temperature in Kelvin, and K is the rate constant. If we manipulate this equation further, we can take the natural logarithms of both sides and get it in the form of y equals mx plus b. Hey, we did this before in the chapter. Once you do this, you can graphically represent the activation energy by taking and graphing the natural log of K on the y-axis and 1 over temperature on the horizontal axis right here. The slope of the line then is the activation energy. So you can find the activation energy by graphing natural log of rate constant versus 1 over temperature. More on that in a future video cast as well. Last section in this chapter are reaction mechanisms. This is the sequence of events that describes the actual process by which reactants become products. It's called the reaction mechanisms. Reactions may occur all at once or through several discrete steps. More than likely, it's through several discrete steps known as elementary reactions or elementary processes. Become used to these terms: elementary reaction or elementary processes or elementary step. There are unimolecular, bimolecular, and termolecular steps. Uni and bi are very possible. Termoleculars are quite rare. In a multi-step process, one of the steps will be slower than the others. The one that's the slowest is the one that determines the rate of the reaction. It is called the rate determining step. You can see here, plaza A of the toll booths is the one that's rate determining. Here, plaza B is the one that holds up the reaction, and they're all slowed down, and so it is the rate determining step. The rate law for this reaction is found experimentally to be KNO2 squared. CO is necessary for the reaction to occur, but the rate of the reaction is not dependent on its concentration. It's called a zero-order reaction in terms of CO. This suggests that the reaction occurs in 2 steps because NO has to collide with NO2 has to collide with NO2. So here's possible 2 elementary steps. A slow step of NO2 and NO2, making the intermediate called NO3, which then reacts with CO. And it's a fast step and is not rate determining. Therefore, this first step right here, labeled the slow step, is the rate determining step for the entire reaction. And notice the stoichiometry, 1 and 1 right here, matches the exponent of the rate law. CO is not involved in the slow rate determining step. It does not appear in the rate law. The rate law for the reaction is found to be this guy. Because a termolecular process is rare, the rate law suggests it must be 2 steps. For this to be true, 2 NOs and a BR would all have to collide with the correct orientation exactly at the right time. Termolecular steps are rare, and therefore it must happen in more than 1 step. Here's a proposed mechanism where the slow step is second. Notice it forms a fast equilibrium right here with NOBr2 in intermediate, which backs up and actually can be replaced by these guys. And so just like in math class where you can take something that's equal to something and substitute these guys in for it, you can do that when there is a fast equilibrium step before a slow step. More on those examples in a future video cast. Rate law of the overall reaction depends upon the rate of the slow step. The rate law for that step would be, but you can't have NOBr2 be in there because they are not, or it is not in the overall reaction. So how can we find it? Well, you can look backwards to the equilibrium step like I said before, and they tell you the rate forward is equal to the rate reverse, which is true at an equilibrium step. Solve for that NOBr2, and you end up with this stuff that we plug in for that. Substituting into the expression, you end up with a new K right here, and then the NOs to the second power and the BR to the first. And like I said, more examples like that in a future video cast. Very lastly, catalysis. Catalysts increase the rate of reaction by decreasing the activation energy. You can see right here it provides a different pathway on the reaction coordinate, a lower one than the uncatalyzed reaction. Notice it also forms an intermediate right here, and there are actually 2 activation energies that have to happen, and therefore it's a multi-step mechanism. But this one right here would be the rate determining step because it would have the highest bump. Catalysts change the mechanism by which the process occurs. One way a catalyst can speed up a reaction is by holding the reactants together and helping bonds break. Right here is a hydrogen carbon on a surface of a catalyst, holding some together, causing one to break, and then allowing it time to stick together. Enzymes are catalysts in biological systems. The substrate fits into the activation site of the enzyme, much like a key fits into a lock, which, if you've taken biology before, maybe you've heard of the lock and key model for enzymes. This concludes Chapter 14, Kinetics PowerPoint. Please watch the other video casts to help you learn more about kinetics.